This is example 3 in section 3.1, analyzing and graphing a rational function. So we're going to simplify the cubic in the numerator and denominator. Because the coefficients in the first two terms are 1 to 1, and then we have a 4 to 4, which equals a 1 to 1 ratio, we can simplify and factor this cubic by grouping. So we're going to look at a common factor for the first two terms, which would be x squared, and you'd be left with x minus 1. We're going to take out a common factor of 4 for the second two terms, and you'd be left with x minus 1 as well. So then you have an x squared minus 4 with an x minus 1, and you have a difference of squares, x plus 2, x minus 2, and an x minus 1. So we're going to place that in the numerator, and then we're going to factor the denominator. This also has a GCF of 2x squared, so then you're left with x subtract 2. We notice that the factors cancel of x minus 2, so you're left with x plus 2, x minus 1 over 2x squared. If you were to expand this, you'd get x squared plus 1x subtract 2 over 2x squared. So let's analyze some of this simplification that will help us determine what's going to happen when we graph it. Because the degrees are the same in my function, I know I'm going to have a horizontal asymptote, and I can look at the coefficients and I know it's going to be a half, but again, you have to prove it. If you look at the simplified function, you still see that half, and that's okay to use the function as well. The factors that canceled, I know I'm going to have a pod at 2, but again, I will prove it. I know I'm going to have x-intercepts from my numerator, and I'm going to have 2 of them. And I know I'm going to have a vertical asymptote at 0 in my denominator, because that's where the function's undefined. So we're going to find all those values using algebra, and then we'll graph it. So our pod, our point of discontinuity, occurs at x subtract 2, where x equals 2. When you plug it back into the function, and again you can use the simplified function, you get 2 plus 2, 2 subtract 1, and you plug in 2, you square it, so you get 4, and 1, you get 8, so you get a half. So we know our point of discontinuity is at 2.5. Our x-intercepts is when you let y be 0. Again, we're looking at the numerator, and I'm going to use the factor form because it's easier to see. So you get -2 and +1. Our y-intercept is when x is 0, so when you sub it into your function, you're going to get 0 plus 2, 0 subtract 1, 2, 0 squared. So you see that you get -2 over 0, which is undefined. Now, undefined just means that when you graph it, you will have no y-intercept. The vertical asymptote is where the function was undefined, which is your denominator. And in the denominator, we had 2x squared. So if we set that equal to 0, we get x equals 0. But now we're going to prove it, the behavior for our function when we graph it, by calculating the limits from the left and the right of 0. So when you use the simplified function and plug in test points, you will determine if it's a positive infinity or if it's a negative infinity. So when we use our test points, we will notice that like 0 from the right would be like 2.1. We notice that we'll get negative infinity and negative infinity on the left as well. So that just tells me that at 0, my function is going to be going down to negative infinity on both sides. We already know there's a horizontal asymptote, not an oblique, and we're going to determine that by getting the limit as x approaches plus or minus infinity of my function. I'm going to take the 2x squared, which is the denominator, and divide it by the highest power, which is x squared. Then I'm going to do the same thing to the numerator, so I'm going to get x squared over x squared, x divided by x squared, and 2 divided by x squared. And you'll notice that these will go to 0, This will go to 1, that will go to 2 because the x squareds cancel. So that's where we get our half. But what we want to do is check to see if the function actually hits the horizontal asymptote. So we take our y value a half and set it equal to our function. And we cross multiply. So when you cross multiply, you get 2x squared equals 2x squared plus 2x minus 4. The x squareds cancel and you end up with 2x minus 4. So this gives us 2x equals 4, so x equals 2. So I know the graph is going to cross at this point, but this point actually is also where my pod is. So when it crosses, you have to show that there is a hole at that coordinate. Our sign diagram is like our x-axis, so we're going to place our x-intercepts, our vertical asymptote, on the graph. So 0 is where I have my vertical. And I'm going to substitute values in that section and this section and so on and see if y is positive or negative. So I know when you plug the values in, you'll get positive, negative, negative, positive. And you can verify that on your own. So when we look at our graph, and I'll just give you one example. If you chose -1, you would get -1 for your y value. So that's how I'm getting a negative. So when you look at your graph, the last thing we're going to do is look at the horizontal asymptote. We see it's a half. We can see the vertical is at 0. And most important, we have a pod at 2.5. We notice that our function is going down, and that verifies that's negative infinity towards 0. We know the function is going to hit the x-intercept and go towards that asymptote. We know that's going to hit the x-intercept of 1 and it's going to go towards it. But this case here, it actually hits it at that pod. But when it hits it, it's still going to go towards it and just level off. But it won't go back down and hit it because we only found one coordinate where it hit. And that's your graph.